I'm Alex Moore.
I'm Ruth Mellin. This is Project Cersei, smartphone-enabled robotic sign language interpreter.
American Sign Language, or ASL, is used by deaf and hard of hearing people and involves changing hand positions, gestures, and facial expressions. ASL interpreters translate between ASL and English to facilitate communication between hearing and hard of hearing people, often in federally funded settings like hospitals, schools, and courts. Interpreters would also be helpful in less formal settings, but generally cannot be present due to timing, location, and financial constraints. Unfortunately, there is a shortage of ASL interpreters due to certification issues.
There are some existing technologies to aid with this problem. Having an interpreter join a video call helps people in hard-to-reach locations, but does not help with the general shortage. Speech-to-text software is a common solution, but text does not allow as much expression or speed of communication. Another option is to use hand-tracking gloves that detect and translate hand posture, but these gloves are very bulky and cost thousands of dollars, making them impractical. An alternative to gloves is computer vision hand tracking, though the software also has yet to reach commercial markets. All of these solutions translate from ASL to English, but none help with the reverse, English to ASL. One solution to this problem is Aslan, a robot hand developed in 2017 which can translate only text into most ASL letter signs. However, Aslan looks unrealistic, is quite bulky, and costs several $100s.
The objective of Project Cersei is to create an affordable and accessible 3D printed robotic hand that can translate speech and text into ASL letter signs as a supplement for situations without human interpreters. Project Cersei has many applications. The simplest is live interpretation, where a hearing person could have their speech spelled out in real time by Project Cersei. A more advanced application would be virtual translation, where a hard of hearing person could have Project Cersei translate what was being said in a virtual meeting. Another advanced application would be communicating virtually with deaf-blind people, who could feel the robot's hand signs while it translated the words of a hearing person connected over Wi-Fi. All of these applications could assist in previously mentioned situations where interpretation is useful but not available.
Here's how we made it work. The non-electronic components of the hand were built following the project of the Instructables user RoboFlex the Citadel, who provided 3D printing files, non-specific assembly instructions, and rudimentary code for single-letter text input. All the parts were 3D printed on a Prusa printer using PLA filament. In order to make the design accessible, parts were then assembled with affordable materials such as glue and metal wire, and common tools such as pliers. Once the hand was assembled, 30-pound Dacron fishing line was threaded up and down through each finger and glued into the fingertips. The line was then tied and glued onto corresponding servo motors with 3D printed pulley attachments in the forearm. Additional components and assembly strategies were developed to make Project Cersei a more complete and functional design. A base to house the electronics was constructed with plywood, which is inexpensive and easy to work with. Supports were designed, 3D printed, and glued onto the base to maintain a vertical arm position. Nail polish was applied to the fingertips to increase visibility in complex positions.
Here's how it works from a software standpoint. The user begins by speaking to an app on their smartphone, which sends their transcribed words to a Bluetooth module. The Bluetooth module then sends this signal to an Arduino Uno. The user can also type what they want to say on a computer that is wired to the Arduino, with the same outcome. This means users can use their preferred mode of communication, meeting the project's goal of flexibility. Code was written for the Arduino to process words. The Instructables creator's simple program was used as a starting point and was eventually entirely replaced with new and improved code. Roughly speaking, the program breaks up text input into individual letters, then maps each letter to a corresponding set of angles. These angles and the order of finger movement are sent to the motors, which rotate and cause the fingers to bend. Then, the fingers revert to their open position and the process repeats. The Arduino sends motor commands to the robot via a servo controller, which is ultimately what tells the motors to move Project Cersei's fingers.
Salutations! To evaluate the success of Project Cersei, each letter was ranked by the co-creators, who are proficient in the ASL alphabet, on a 5-point scale that was developed. A rating of 1 corresponded to cannot perform, a rating of 2 corresponded to performs poorly, a rating of 3 corresponded to performs acceptably, a rating of 4 corresponded to performs well, and a rating of 5 corresponded to performs perfectly. The accuracy was considered relative to a human hand performing the same sign. The top graph shows the initial data using the code created by the Instructables user who published the design for the robot. With the initial program, half of the alphabet could not be performed and only 8 signs received a high score of 4 or 5. The code was then improved to fine-tune the motor angles, and new code was implemented to move the motors in different orders, allowing for letters such as M, N, and T to be performed. As seen in the bottom graph, the new code greatly improved the accuracy of the hand, as 4 new letters could be executed and nearly half the alphabet received a 4 or 5.
Project Cersei met its stated goal, to translate text and speech into American Sign Language. Several other major benefits were noted, none of which were present in the initial Instructables design. First, Project Cersei is 100% consistent. This means that it replicates finger positions precisely, without fail, and never skips letters that it receives as input. Project Cersei is able to sign at 40 signs per minute. This is only around 50% slower than a reasonable speed for human ASL users, and a doubling in speed could be achieved with minor software improvements and servomotor upgrades. Project Cersei is also very easy to transport, as it weighs only 3.2 pounds. It also looks fairly realistic compared to existing alternatives, making for more organic communication. Finally, Project Cersei has a material cost of less than $100 and could be easily assembled with few tools by an unskilled user, making it extremely practical as a commercial product. Project Cersei has 2 main drawbacks. First, the motors are somewhat loud, which could be bothersome to users. Also, it cannot perform 1/3 of the alphabet due to wrist and finger joint limitations, though most of these letters are less common, like J, Q, and X.
There are many ways to improve Project Cersei to be a more comprehensive interpretation system. Hardware developments like a fully articulated wrist and finger joints that move independently from one another will improve the accuracy of many signs. These developments will also enable the performance of previously impossible letters such as G, J, and P. Additionally, upgraded motors will be used to control the motion of the fingers, which will make Project Cersei faster and quieter. A custom app will be developed to streamline the interface between speech and text to ASL translation. Finally, computer vision sign recognition will complete the 2-way communication loop by translating from ASL signs to English text. With all these developments, Project Cersei has the potential to be a comprehensive translation system which could alleviate ASL interpreter shortages.